Previously, we discussed moving vehicle tracking using RF technique using Kalman Filter. For this second video, we will talk about the extended Kalman Filter for moving vehicle tracking. So this is a second in the 3 video series, okay? And for more information about moving vehicle tracking, Kalman Filter, and applications, please refer to the previous video, and we give you the link on the introduction slide. Extended Kalman Filter is useful for nonlinear systems, and RF noise by nature are nonlinear and non-uniform. And noise sources can come from several things. Analog components used in the system can also have noise, and variation in thermal or voltage can create noise in the IF system. Weather is a significant noise generator for communications and IF systems. And if the frequency band is being overused by too many people and too many different transmitters, there will be noise. And there are also intentional noise generated by others. So jamming is a major contributor. And to measure distance and angle from a point to the unmanned aerial vehicle usually is very noisy, and those noise are nonlinear using RF technique. And differential equations are used to modeling those type of measurement, and typically those contain trigonometric functions or higher degree polynomials. And so the systems or the measurement representation are nonlinear. The regular Kalman filter is intended for linear systems, so they cannot be used in nonlinear applications. And extended Kalman filter is designed specifically to handle that, and it's more compute intensive. I will explain the demo a little bit. The demo here is very similar to the previous one, except that it is designed for nonlinear. So the first part, we also will track a UAV from the US West Coast to go to the north and then go down to Florida. It will use tracking with linear XY coordinates, latitude, longitude. But the measurement data are going to be given in distance and angle. These are uniform data, but a uniform error, but they are non-linear in terms of noise. And then the second part, instead of using distance and angle, we will convert that into XY coordinates and before applying the extended Kalman filter. Here, we're talking about XY coordinates, but in terms of longitude and latitude, we need to take into account of the curvature of the Earth, and the model that we develop and the data do take care of that. And the third part of the demo is more realistic modeling of using non-uniform measurement and non-linear error conditions for distance and angle measurements. So the next part here will show you the demo.
In the previous video, we saw the simulation of flight tracking system with Kalman filter. However, one of the limitations of Kalman filter is that it requires the state equations and the measurement equations to be linear. So if one of the state equations in the filter or the measurement mapping to the state is nonlinear, then we cannot use the Kalman filter. For this purpose, we need to use extended Kalman filter, which uses partial derivative equations to linearize the state or measurement equations and then estimate the true values of the measurements. So we will use the similar setup that we used in the previous demonstration. So the system will plot the flight path on the map that is shown in the screen. And now we will see the simulation of extended Kalman filter. Now I have started the simulation of extended Kalman filter system. The system configuration is still the same in the sampling time of 1 second. The system state that we are using is xy coordinate and the velocities along xy coordinates. So the system state equation still remains linear. However, as you can see in the system measurement section, we will be using rho and phi, which is the straight line distance of an object or flight and the direction of the object. So in this scenario, the system measurements are related to the system state with nonlinear equations, which are trigonometric equations involving sine and cosine functions. So in this case, we will need to use extended Kalman filter with modifications in equation using partial derivatives. So we will start the simulation now and see the results. Now the system is plotting the noisy measurement across the map shown on the screen. As you can see in the sky blue color, we can see the measurements being plotted, and which is make it very difficult to estimate the actual flight path. Now on this next graph, we are seeing the Kalman filter estimation. So this is an estimation from extended Kalman filter. So considering the nonlinear measurements of radar, that is distance and angle, we are still able to plot and estimate the actual XY coordinates. Now in the right hand side figure, you can see the measurement and estimation error and their comparison. As you can see, the estimation error is still significantly reduced from the measurement error. And on the command window, you can see the result of root mean square errors for both measurement and estimation of x and y coordinates. So this was one method to to deal with the nonlinear equations in the flight path tracking system. So now I will show you the another way in which we can use the extended Kalman filter. So in this case, we will be using the same system state as before, that is xy coordinates and xy velocities, but the system state matrix also remains the same. But this time the system measurements are going to be the radar measurements, but they will be internally mapped to the x and y coordinates by the system. So from outside the system, we are using the distance and angle as the measurements. However, internally they will be mapped to the xy coordinates. And now we will see the results of this method. So now the system is again plotting the noisy measurements first. And now we can see that system is plotting the Kalman filter estimation. Now we can see the final errors being printed. Now to actually compare these two different configurations of using extended Kalman filter, we will go to the result log file. So in the most recent runs, we saw the working of extended Kalman filter, which uses the state vector of xy coordinates and xy velocities, but it uses the radar measurements of distance and angle. Now, as we saw in the Kalman filter demonstration, the error in the measurement is still uniformly distributed. So we will need to test the extended Kalman filter with the non-uniformly distributed error in the measurements. So now I am running the same extended Kalman filter as before. So it will use the measurements of distance and angle, but this time the error will be nonlinear. So I will skip ahead to the simulation. So now you can see the noisy measurements being plotted, which are non-uniformly distributed across XY plane. It is more difficult to visually estimate the flight path in this scenario. So we will now see how extended Kalman filter performs in this case. As you can see, there is some initial error for the extended Kalman filter, but once it converges on its path, we are getting a pretty good estimate of the actual flight path. And now we can see the final results. We can see the non-uniform errors being reduced after estimation. Due to non-uniform distribution, the error magnitude of the or root mean square error is slightly more than before, but we are still able to significantly reduce this error after applying extended Kalman filter to the measurements. So in this scenario, we have successfully demonstrated the ability of extended Kalman filter to filter the noise in nonlinear measurements and nonlinear systems. Thank you for watching.